Welcome to this rapid review explainer. I'm going to be your tutor today, coaching you through the high-yield concepts of stress, strain, and material mechanics. Look, if you've got a physics exam coming up and you really need to lock down exactly how forces deform the solid world around us, you are absolutely in the right place. We're going to break down everything from the classic equations to real-world structural engineering and guide you straight to the facts you actually need to know.
So, here's our game plan. We'll start with the core concepts of elasticity and plasticity, decode the essential math and stress-strain curves, and then tackle some real-world applications before walking through a classic homework problem together.
All right, let's jump right into Section 1, elasticity, plasticity, and hook.
To really understand material mechanics, we got to look at how things deform. It's pretty intuitive, right? An elastic material, like a spring, completely snaps back to its original shape and size the moment you stop pulling it. It has this built-in restoring force. But plastic materials, well, think of a lump of putty or wet mud. They suffer permanent deformation. If you press your thumb into mud, it doesn't bounce back. That fundamental difference between snapping back and staying smashed, that's the difference between elasticity and plasticity.
This brings us to a massive, absolutely crucial concept for your exam, Hooke's law. Back in the 17th century, Robert Hooke figured out that for small deformations, and remember that part, small deformations, the restoring force per unit area, which we call stress, is perfectly proportional to the fractional change in dimension, which we call strain. Put simply, stress equals a constant k times strain. That k is the modulus of elasticity. It's an empirical law based on observation, and it works for most, but totally not all materials.
Moving right along to Section 2. Decoding stress-strain curves.
To figure out a material's true, ultimate strength, structural labs literally map out its entire life cycle. Imagine hooking a test wire into a machine and just slowly increasing the pulling force. Initially, the graph shoots up in a perfectly straight line. That's Hooke's law in action. But eventually you hit a yield point, the elastic limit. If you push past that, the wire won't spring back anymore. It's got a permanent set and enters plastic deformation. Keep pulling and you hit the absolute peak of the curve, the ultimate tensile strength, before the whole thing finally snaps at the fracture point.
Now, you're definitely going to be asked to interpret these curves on your test. Pay close attention to the gap between ultimate strength and fracture. If those 2 points are squeezed super close together, the material is brittle, kind of like glass. It just shatters almost as soon as it hits its max strength. But if those points are far apart, the material is ductile. That means it's going to stretch and deform significantly before it finally gives way.
Okay, time for some math. Section 3. Young's, shear, and bulk moduli.
Consider this your ultimate exam cheat sheet for matching deformations with their specific moduli. If you're dealing with pulling or pushing, changing the length of a cylinder, you use Young's modulus, denoted by Y. If you've got tangential forces causing a shape to skew or shear, you use the shear modulus, denoted by G. And if an object is dunked under hydraulic pressure, shrinking in volume from all sides, you use the bulk modulus, denoted by B.
Listen up, because this is a classic trick question that catches almost everyone off guard. In everyday life, we say rubber is super elastic, right? But in physics, no way. A material is considered more elastic if it requires a larger force to produce a tiny change in length. So actually, steel, with its massive Young's modulus of 200 gigapascals, is far more elastic than rubber. Elastomers, like rubber bands or even the aorta tissue in your heart, stretch enormously without obeying Hooke's linear law at all, meaning they actually have a very low Young's modulus.
Oh, and you can't forget Poisson's ratio. Think about it. When you stretch a wire lengthwise, it doesn't just get longer, it also gets thinner in diameter. Simon Poisson pointed out that this lateral contraction is proportional to the longitudinal stretch, because it's literally a ratio of two strains, a length divided by a length. Poisson's ratio is just a pure dimensionless number that describes that lateral squeeze.
Here's another high-yield formula you gotta lock down: elastic potential energy. When you stretch a wire, you're actively doing work against the inner atomic forces holding that metal together. This formula, U equals 1/2 times stress times strain, shows exactly how that mechanical work gets stored internally as the elastic potential energy per unit volume. It's honestly the exact same principle as drawing back a bowstring.
All right, let's step out of the lab and into the real world. Section 4. Real-world structural engineering.
Have you ever looked at a bridge or a skyscraper construction site and wondered about those distinctive I-beams? Why go to the trouble of manufacturing such a complex shape when you could just use thick, solid rectangular blocks of steel?
Well, it's an absolutely ingenious geometric compromise.
The math shows that increasing a beam's depth prevents it from sagging in the middle when a heavy load is applied. But if you just make a really tall, thin bar, it's going to buckle and twist sideways. The I-beam shape brilliantly maximizes that load-bearing depth to stop the downward sag, while those wide top and bottom flanges prevent catastrophic lateral buckling. Plus, it significantly cuts down on weight and cost compared to a solid block.
Here's another fun one to test your intuition. Look at any heavy lifting crane. The steel ropes are always braided from dozens of smaller wires. Why not just cast one single massive steel cable and call it a day?
It all comes down to yield strength versus flexibility. To safely lift a 10-ton load, the math tells us we need a solid steel cylinder with a radius of about 3 centimeters. But think about it. A 3-centimeter thick bar of steel isn't a rope. It's a completely rigid rod. You could never wind that around a crane's pulleys. That's exactly why steel ropes are braided. You get the cumulative tensile strength of the solid rod, but you keep the flexibility you need for mechanical windings.
Let's scale things way up to geophysics. Based on what we now know about stress and strain, why don't we have mountains on Earth that just infinitely pierce the atmosphere? Why do they always seem to cap out around the height of Mount Everest? This is literally a massive display of shear modulus on a planetary scale. A mountain isn't just pushing straight down. Its unimaginable weight creates this intense shearing stress at the base, where the sides are unconstrained. The elastic limit for typical rock is about 30 times 10 to the 7th newtons per square meter. Plug that into the density and gravity equation, and you find the maximum height before the rock fails is roughly 10 kilometers. Mount Everest is right near this limit, because if it were any taller, the extreme shear stress would cause the solid rock at the base to permanently deform and just flow outward like plastic mud.
Okay, home stretch, Section 5, exam prep and a homework walkthrough.
When your exam throws a curveball and asks you to calculate something crazy, like the compression of ocean water in textbook example 8.5, don't panic. Just follow these 3 easy steps. First, find your hydraulic pressure by multiplying the depth, 3,000 meters, by the density of water and gravity. Second, recall the bulk modulus of water, which is a constant 2.2 times 10 to the 9th. Finally, just divide that immense pressure by the bulk modulus to find your fractional compression.
Run those numbers perfectly, and you get a fractional compression of 0.0136. Think about what that means. Despite the unimaginably massive weight of a 3,000-meter water column pressing down from literally every side, the actual volume of the water at the bottom of the Indian Ocean only compresses by a tiny 1.36%. Water resists hydraulic compression incredibly well.
To wrap this whole explainer up, I want you to memorize these high-yield points for your test. First, stress is not a vector quantity. Unlike force, you cannot assign stress a specific single direction. Second, remember our tricky physics definition of elasticity. Steel is more elastic than rubber because it fiercely resists deformation. And finally, hydraulic pressure behaves vastly differently across states of matter. Solids are tightly coupled and nearly incompressible. Liquids are loosely coupled, but gases are about 1,000,000 times more compressible because their molecules are completely isolated.
I really hope this rapid review leaves you feeling totally confident to ace your exam. You've got the concepts, the formulas, and that real-world intuition down. But I want to leave you with a fascinating final thought. As engineers start creating futuristic synthetic metamaterials in labs today, how are these age-old classical formulas going to adapt when we create substances that completely defy standard elasticity? Keep that curiosity alive, guys, and good luck on the test.